The way we do that for what's called key point localization, and key point and interest points are used similarly. Key point was the term used by David Low in SIFT. We'll talk about that in a minute. Here is the general idea. We want to find robust extremas. So maximums, by the way, you can also find minima. So if you remember for the Laplacian, it goes through 0, goes positive, negative. So if you took the absolute value of that, say, the square, the value that's 0 is a good point. Anyway, you want to find robust maxima and minima in both space and scale. So that's what's drawn here. We haven't talked a lot about scale space, but the idea is, I have an image, and then I could filter that image again, and I could filter it some more, and you can think of it as a coarser and coarser scale. And I have some point, and you can think of that point as having neighbors to the left and right, and you can also think of that point as having neighbors up and down in scale, and that's referred to as scale space. A specific way of using that scale space was suggested by David Low in the SIFT paper. But at that point, there was a specific suggestion of do this difference of Gaussian pyramid. What I mean by that is you do it at different scales and over space to find maximum values in all those. Now, sometimes you might land along edges. Okay, so you're on a maximum value, but it's really just the maximum along an edge. So what you have to do is you have to eliminate the edge points. In fact, if you recall, we first introduced Laplacians of Gaussians to find edge points, right? Even though it was a circularly symmetric operator, you were able to find these edges. So from way back, from the Harris, we said, well, edges aren't so good for finding specific locations. We want it to be more like a corner. So basically what you would want to do is you would want to find points that have these extreme values, then make sure that thresholded, that they were extreme enough, if you will, and then make sure they're not edges. So here was a particular method by which it was done, and I show you this so you can take a look at the results in a minute. Basically, what was done was you take your image and you deal with it an octave at a time, and an octave is a doubling. So what you do is you make it blurrier and blurrier and blurrier and blurrier. Then you take half, then you reduce that down to half the size and make it blurrier and blurrier and blurrier and blurrier. And what you do is you subtract these off to get your difference of Gaussian images. Then within each one of these Gaussian images, you're going to compare a pixel. And in fact, if I go back to this picture here, I'm going to compare this pixel to each of its 8 neighbors, and each in the same plane, and there are 9 neighbors above it and 9 neighbors below it. And if you're a maximum of that, you're going to say, aha, I'm an extrema.